This is Kiara. She tends to have 10 different applications open at once, leading to what we call overheating. Don't be like Kiara and invest in CPU cooling, specifically ones that look at different heat sink types. As the digital age arrives, we now see that there's much more a need for faster and smaller technology and electronic devices as before. This means that we want smaller electronic processing units, such as CPUs, but ones that can still give us the same processing power. This leads to what we call overheating. A CPU, or central processing unit, is a device that runs all of the hardware and activities on a device such as a computer. The CPU carries many different tasks at once, and although it can effectively and efficiently carry out these tasks using just the cooling system of the device, there does come a time where this cooling system can become exceeded, known as thermal design point. This is the maximum temperature for a cooling system in a device. Once this is exceeded, overheating occurs. In order for us to counteract this overheating, to ensure that the CPU and the device works efficiently and reliably, we then take into account CPU cooling. CPU cooling makes use of a fan, thermal tape, and a heatsink. Heat sinks are what cause the main part of our heat transfer in the CPU cooling system. It allows the heat transfer between the hot and cool air. The hot air is then dissipated over the surface area of the heatsink, and then the cool air then is allowed into the CPU unit. Heat sinks help with dissipating hot and cool air over the surface area, which helps enhance and increase the heat transfer between the hot air and the cool air, allowing for more efficient CPU cooling. Heat sinks are also much more affordable and reliable than any other form of cooling systems for electronic devices, but the performance of heat sinks depend on its material. Most commonly is copper and aluminium. Its configuration types, such as a round or a plate heatsink, as well as its thickness of the fins of the heatsink, all interfere with the heat transfer rate that can then assist with the cooling system. In this report and in this video, we'll be investigating round and plate heatsink effectiveness. We will look at the different temperature simulations using SimScale to see which is the most effective in CPU cooling, so that you may have the most efficient and reliable device to use.
Our aim was to compare the efficiency of two heat sinks that have different fin geometries. The chosen geometries were the flat plate and aligned pins. Both of these heat sinks will be dissipating heat from a CPU. Before getting into the simulation, the system and method needs to be validated. This was done by obtaining a simulated solution and analytical solution to a simple tube bank force convection problem. The results yielded an error of less than 10% when a mesh value of 3 was used during a conjugate heat transfer simulation. Modeling a CPU is complex, so simplifications were made. The CPU was modeled as a thin silicon solid with isotropic properties. The inlet was also modeled as a free stream instead of a fan. In order to compare different geometries, we need to keep all other parameters the same. The environment for both heatsinks has to be identical. Research was done on the CPU units, fans, and operating conditions. It was found that most CPUs produce about 85 watts of power. The most effective heatsink material is copper, and the average mid-range fan speed pushes air approximately 15 meters per second. These parameters were applied to both heatsinks. In terms of simulation, the conjugate heat transfer simulation was used because it is capable of simulating the interaction between fluids and solids well. Using a mesh value higher than 3 was very time consuming. The validation produced pleasing results with this value, so we used the same value to run both simulations.
Looking at the results for this plate heatsink, it can be seen that the temperature is dissipated towards the sides of the heatsink as well as between the plates of the heatsink. Looking at the results for the circular pin heatsink, it can be seen that the temperature is highest closest to the velocity inlet and at the sides. Looking at the bottom view of this plate heatsink, it can be seen that the temperature distribution is highest between that interface of the CPU and the heatsink. Looking at the results for the circular heatsink, it can be seen that the temperature is also highest. The temperature is also highest at the interface between the CPU and the heatsink. It is, however, a little bit lower than that for the plate heatsink. Looking at the overall results for the plate heatsink, it can be seen that the hot air rises and is dissipated mostly at the top, as was previously seen, where the heat was dissipated between the plates of the heatsink. Looking at the overall results for the circular heatsink, it can be seen that the temperature also rises towards the top and is hottest at the top of the heatsink.
Under this section, I'll be discussing the results and what they mean. So for our first observation, we're going to discuss the plate pattern heatsink, by which air that is passed through is emitted at a higher temperature in comparison to the circular pattern heatsink, by which air is emitted at a lower temperature. Another observation that can be seen is by which air is not easily cooled through the circular pattern heatsink, and this can be seen by the temperature that is concentrated at the center of the CPU, whereas in the plate pattern heatsink, the temperature gradually increases through the fins. This makes it easy for the airflow to dissipate the heat through the fins. And it is through this observation that we can further conclude that the plate pattern heatsink conducts heat better than the circular pattern heatsink. The conduction of heat further justifies the better efficiency for the plate pattern heatsink to dissipate heat better than the circular pattern heatsink.
The next section that we'll be looking at is the conclusion section. Firstly, the overheating of CPU has become more and more problematic over the years, especially now that computers have become smaller and smaller. Therefore, there is a very big need for a cooling system that will cool the CPU to the required or optimum temperature level. The use of heat sinks can be one solution to the problem of overheating to the CPU. In this experiment, two heat sinks in circular pin fins and plate fins were analyzed to gauge how well they can cool the CPU to the optimum level. This was done using CFD modeling on SimScale. Both heat sinks managed to lower the temperature of the CPU to the required level. However, the circular pin fin heat sink performed better than the plate heat sink, as it managed to lower the temperature of the CPU more than the plate heat sink. The next and final section that we'll be looking at is future work. This is work that can be done in the future to improve the results of the experiment. Some limitations were found during the experiment which could have affected the final results. This should be dealt with in future to produce more reliable results. This includes the limitation regarding the simplified heatsink model. Only a copper heatsink and a single silicon CPU were used. More materials should be used to produce more reliable results in future. The inlet and outlet flow regimes were also simplified, where the inlet was modeled as an inlet velocity instead of a real-life fan. With more computing power, a much realistic fan configuration can be used. The final limitation about the experiment is the thermal interface between the CPU and the heatsink. This was not considered during the experiment, and it can have major implications on the thermal conductivity between the CPU and the heatsink.